Welcome to the PES live stream. If you can hear me or you're here, please just say hi in the chat and we'll get started very shortly. Turn that off. So if you're here, just put something in the chat to mention that you're here, and then we'll start talking about some concepts. I'll find my pen. So I'll just make sure everyone can hear me. If you can hear me, say so in the chat. And if you're here, just say so in the chat. Why is this not working? It's not connected. There we go. Cool. All right. So if you're here, just say hi in the chat. I'm just waiting on a couple more people, and then we will get started on a couple of things. My plan for this is to go over some concepts first, and then go over some stuff in the assignment. I think this is a good way to approach this, and that means that everyone will be on the same page. I won't recover pointers unless we need to, but we'll be going through stuff involving pointers, so it'll be a recap on it anyway. So let me just grab this list. So what I'm thinking is, now there are videos for this, but let's go over it anyway. I'm thinking, let's get rid of this first. And this, I don't know why that's there. So I'm thinking we'll look at null pointers. We'll look at arrays with pointers. We'll look at the stack and the heap quickly, just really quickly. Then we'll look at dynamic mem. We will look at probably somewhere here, we'll look at pointer arithmetic. And yeah, I think then we'll go on to the assignment. Unless anyone's got anything they want to chat about. Let me move the chat out. Oh, that's pretty good. Let me see if I can find this example. I had a nice example that I was going to use. I made earlier, but I think I've lost it. Thousands and thousands of files. What did I call it? What are we doing? Pointer arithmetic. Oh, shit. I want to go back into that folder. You go .c. This month. I know I should be able to find. There's lots of assignments. Forgot about that. All right, I'm just trying to find an example I want to use, because then I can copy and paste it in rather than retype it or handwrite it. All right, we're starting to get some more people. So while you join, just say hi in the chat. This is just makes it easier for me to know that you're here and that you are listening. Just trying to find a file. Why is this so difficult? Awesome. So we've got quite a few people, which is good to see. Where is this file? Okay. Could be in here. No. That's strange. Oh, we will rewrite it. That's all right. All right. So I'm going to go through this here, if everyone's okay with that. So the first thing I kind of wanted to cover was null pointers because they're kind of really handy. So if I did something like this, let's say, and I go int star pointer, and then I did printf %d dereferenced PTR. Now, this here is bad, okay? Because obviously PTR, we don't know what it's pointing to at the moment. So we've got A, which is well-defined. Okay, so we've got A, which is an int. It's got the value 4, but we create this pointer. And what we've got to remember about C is that when we create a variable, we don't know what's inside it. Sure, we can have a look at the exam answers. Yeah, I can put them up a little bit later. If I forget, just remind me. I usually try and leave that till later. If there's a particular question, that might be better. We'll come back to that. All right, so this here, if I dereference it, it could have any value. It could be 1111, it could be A48, it could be any address whatsoever. And if I go and dereference that, then I could get lucky and get a value that prints out here. Maybe I could even get the value 4 to print out from some other location in memory. But considering how large memory is and how many programs are running on it and how small our program is in the grand scheme of things, it's most likely going to crash. Okay? It's most likely going to crash. Okay? Okay. Now, this... So someone said it'll print out a garbage value. If I did something like this, if I did printf %d a, and I didn't initialize a, then yes, I'm definitely going to get a garbage value, okay? Because I don't know what's inside of a, okay? All right. But here, I've actually got a worse case because it's not that it's going to print out a garbage value. It's going to go to some random memory address and try and read it. And if we remember back to the lab this last week, we don't want to touch other bits of memory that are in use because they will crash our program. So let's say this piece of memory is 85 or something, and randomly it's 85. As soon as it goes to read this, it's going to crash my program. Okay, so having it uninitialized will most likely crash my program. Now, whilst this is fairly detectable, the biggest problem here is that this part. Okay, it's not the fact that it crashes that's the problem. It's the fact that we don't know if it will crash or won't crash. Because if it doesn't crash, we will miss this mistake. Okay, and then when we run it again, it might crash, or if we run it in the future, it might crash. And we don't want that. We don't want this most likely to crash. We want either always going to crash or never going to crash. Okay, we don't want this undefined behavior where we don't know what's going to happen. Okay, so usually going to crash is not good enough. Okay, we want it to crash so we can identify that there's a problem. We don't want something that might crash and we'll never be able to pick it up. So one way to force things to crash when things are wrong is by, we're using, I'm just trying to remember. We're using C, so it's going to be null. All right, so here we have null. Okay, now basically what null does is, sorry, I got distracted. Give me a sec. All right, cool. I've got the chat back. All right, no one said anything anyway. All right, so this null here, basically the way I like to refer to it is no address. Okay, now if you ever try and dereference null, it will always crash. Okay, so if you accidentally use your pointer before it's meant to be used, it will crash. This line here now won't usually crash, it will always crash. And as soon as you see that crash, you can actually debug the program, find out where it crashed, and solve that problem. Okay, so by setting it to null, we're basically saying there's no address at this point that it's storing. Okay, now the other good thing about that is now it becomes testable. So for example, let's say I'm using a bunch of pointers, and let's say it's a little bit more complex than this, and I need to see if there's a pointer that's free that I can use. I can basically say if ptr is equal to null, then maybe I do ptr becomes the address of A. Okay, so if it's free to use, then I set it to A. Okay, so now it becomes testable because at this stage, I can't say is ptr some random value. That won't work. Okay, I need to have a value, and I don't want to give it a particular address. I don't want to write in here 0x01 or something like that, because that might be something that's actually used. Okay, so instead I can say null, and now I can check if that bit of memory is being used or not. In previous assignments that we did in the past, we used this quite a lot. We did a game of Minesweeper, and some of them pointers would be null because they hadn't been uncovered yet, and then we'd point them to the right location once they've been uncovered. And it was a way of tracking if our pointers were actually pointing to something or not. Okay, does that make sense? If that makes sense, just say yes in the chat, and then we'll go on to number 2, which is the big one. And I'll just move this across because I want a particular example. So if that made sense and you're all up to track, just say yes in the chat, or if you want some further clarification, just say further clarification, or don't care, or whatever you want. I want this example. Awesome. So it's a good idea if you're not going to use your pointer straight away, just set it to null. It's a handy little thing to have. And we'll also be using it a little bit later when we get to dynamic memory. All right. Yeah, so if you can initialize it, so if you know that it's going to take on the address of A, then always just set it to something known straight away. Okay, but if you don't know that, then just set it to null. Okay. Yeah, so if you use it straight away, then definitely you don't need that. But if you're not going to use it straight away, then you can set it to null. Some cases you won't be able to set it straight away to null, which we'll see not right now, but later. And you'll have to do some tricks if you want to set it to null, but that can wait. All right, so now what we're going to do is we're going to look at arrays and pointers. And the reason for this is because we want to see some stuff, pointers and arrays. So what I'm going to do is where's my thing? All right, cool. That's the other thing that I wanted to mention. This one's kind of easy. I don't know if I've mentioned this already, but I might have or might have not. At any time in your program, if you want the size of a type, there's an operator called sizeof that you can use. It's not a function. It's actually an operator. So, for example, if halfway through your program, you want to know what the size of a car is, I can just create a variable. I'll just call it value for this example. It's not very useful for storing, but we're going to use it for some maths a little bit later. But I can do size of car here. And you can see quite clearly that this isn't a function because that's a type there. And this will basically get you the size in bytes. So this would be 1 byte, for example. Okay, and if I had int in there, it'd give me 4. If I had short in there, it'd give me 2, and so on. So you can play around with that, but we'll need that shortly. Okay. So all size does is gets the number of bytes of that type back. All right. So now what I'm going to do is I'm going to introduce arrays again. Okay. We've seen arrays already, but this time it's going to be a little bit different. So let me grab this. All right, so what's the best way to show this? I'm not going to bother drawing any memory diagrams this time. There's a video that you can watch if you want. But basically in memory, our arrays are guaranteed to have all the data contiguously. Okay, so meaning that index 1's data will be here, index 2's data will be here, index 3's data will be here, and they'll just keep going down. Okay. If they take up, if let's say we've got an array of ints, this would be 4 bytes, this would be 4 bytes, this would be another 4 bytes in memory. Okay. So with our arrays, you're guaranteed that everything comes one after each other. And that's an important concept with arrays. Now, what I'm going to do is I'm going to declare an array. Okay, so I'm going to go short. I'll call it. I'm going to call it my array, and I'm going to make it kind of short because I don't want to have to draw a lot of boxes. So I'll make it 5. 5's a good number. And here, what I'm going to do is I'm going to put some values in it. 1, 2, 3, 4, 5. Okay. So I've got my array. This isn't anything new that you haven't seen before. But what we're going to have a look at is some useful information about our arrays. So I think rather than using a memory diagram, we'll go straight to box and pointer diagrams. And we'll have a look at how our arrays look like in memory, okay? Because they're a little bit more interesting than we first covered. So I'm going to draw the box and pointer diagram. Now, this is my interpretation of the box and pointer diagram for arrays. So this is my standard, but you can have lots of different standards of this stuff. So we've got my array. Okay, it's an array. It's of shorts. And we've got the values 1, 2, 3, 4, 5. And then you'll also notice this guy here. Okay. So in terms of memory with my array here, if I went into memory, okay, let's say I've got this block of memory here. The actual values, so the 1 would be stored across 2 bytes. The 2 would be stored across 2 bytes. The 3, then the 4, and then the 5. Okay, so they're contiguous memory. They come one after each other. Now, what you'll notice here is this little dangling pointer. And we'll have a look at that in a second. So what I'm going to do is I'm going to set up some pointers. Okay. And these pointers are just like you did last week. They're nothing too interesting. They're fairly basic. So I've got a pointer to a short. I'm going to call it PTRA. And I'm going to take the address of my array, sorry. Let's say 0. Okay. And then we just get a pointer, which is pointer A, sorry. And it's just short star. And what address is it taking? It's taking the address here. Now you have to be careful when using this box and pointer diagrams because that's pointing to the address of this one, not the 2, not the 3, not the 4, and not the 5. Okay. So from here, you can see that our pointers act exactly the same as before. There's nothing too special about them so far. The big difference here is when we go and use this next thing. So here I'm going, actually, we'll do one more example and then I'll do the next thing. So I'll do pointer B, my array. And we'll talk about how to evaluate these square braces because the square braces are actually a little bit complex. but if you understand them, it will help you out a lot. Okay, so we've got a short star. Now this one here is pointing here. Okay, remember that our index started 0, so this is index 0, 1, 2, 3, and 4. Now, from here, I'm going to do something a little bit different. So I'm going to create another pointer, and I'm going to call that pointer C. And I'm going to give that the address, my array. Okay. So this here is a little bit different. And what this does is it actually gives the address of the entire array. But what we remember from our rules about our variables is the address is always the first address. So it's actually giving the address of this first element. So pointer C is going to point at the exact same point. Now, there are some complexities that we can get into and the difference between the two, but for now, we're not going to worry about that. We'll just look at that. So someone asked about the ampersand in front of it. That's where it gets a little bit more complex. You will get the exact same value, but in terms of what they're looking at, it's a little bit different. So we'll leave the ampersand out for now, and we'll talk about it. Initial address is within the name of the array. Yes, so that's what I'm saying. So this little dangling pointer here is the way I like to show this. This will always point to the start because remember that the address of the 1 is always the first address. The address of the 2 is always the first address. So the address of the whole array is also the first address. So my array refers to this whole thing, and it's a pointer right to the start. Okay. Now, if we talk about the address of my array, we're talking about the address of this guy, which gives us the same value as well. Okay. So if you want the starting memory address of an array, you can just refer to its name. Okay, and this is going to be quite powerful, and we'll need this later. And this will allow us to pass arrays around. Because we've noticed already that when we use pointers, we're able to pass these variables around using pointers. But what if we wanted to move around this whole array and keep the information together? Well, now we can use pointers, especially this one, to pass that whole information around. And this is going to be very powerful. Okay. So if that makes sense, let me know. If it doesn't make sense or you want something clarified, let me know. And then we'll keep going. Oh, let me move this. I'll just give it a minute. I'll just make sure that made sense. Does passing the pointer include the type? So when we pass the pointer, we just do it like we did normally. We have one limitation, which we'll have a look at in a second. No, definitely not. If you put the square brackets there, it won't compile. Okay, that doesn't actually mean anything if you put the square brackets there, and it's actually wrong. So no, you can't put the square brackets there. We're talking about this pointer, and that's why I don't put the square brackets here. And I just put this here so that you know the name of the variable, because the square brackets are actually quite complex, as I said before. We'll look at some of the complexities of the square brackets, and we'll do that probably right now. So the square brackets. So let's have a look at this first. So let's say I've got a pointer A, and I'm going to print out this. So I'm going to go printf %d. I'll put a new line so that it's correct. There's no return carriage. And then I'm going to do dereference pointer A. What does that print? So I just put in the chat what it prints. And while you do that, let me do this. I wonder if I can get a line. I think I can. Yeah, I can. So I'm just going to make this a little bit neater. Because I kind of need it. All right. So what value would it print? So remember, when we dereference, just follow the line and go to the value. So I'm just going to call this, let's say, B0, B1, B2, B3, 4, B5, B6, B7, B8, B9, BA, BB. So we dereference it, and it's just going to print out 1. Okay. So same rules as before. We just follow the line, and we'll reach that point. Okay. Now I've just redrawn this. I've got some memory addresses. The first memory address is B0, then B1, then B2. And in the first 2 bytes, because we've got a short, we've got the number 1. In the second 2 bytes, we've got a 2, then a 3, then a 4, then a 5. So I'm going to do something a little bit strange now. I'm going to go pointer A becomes pointer A plus 1. Now, if we think about this logically, I'm at B0, so adding 1 would bring me to B1, wouldn't it? And I'd be printing something when I dereference it in the middle of 2 values. But this is not how it works. And this is really, really, really important to understand. So here where I've got pointer A plus 1, what it's actually doing here Okay. So what you write is this. What it does. Okay. So if I change this to a 2, let's say, what you write is this, but what it actually does is this. Okay. So what's this times 2? What is this times 2? Where did this come from? So this times 2 is actually the size of the thing that it's pointing at. Okay. So pointer A is of type short star, so it times or it multiplies it by the type that it's pointing at, which is a short. And this is the power of pointers, and this is what's known as pointer arithmetic. Okay? The fact that if I add 2, it doesn't add 2 in terms of addresses. Okay, remember that pointer A currently has B0 stored in it. If I add 2 to that, you'd imagine that I'd get B2, but I actually get B4. Okay? And what it's doing is that it's incrementing in the size of the type. So plus 2 is going from here to here, going across, and then arriving here. Okay? But we don't write this multiplication, okay? Because if you do, then it's going to multiply that by the size of as well, okay? So you don't actually write it, okay? So don't write this yourself, okay? This is what it does. This is what you write. When you add 2, it will multiply that addition by whatever the size of it is that it's pointing, which is really, really helpful with arrays, because that means that I can add 1 and end up here. I can add 2 and end up here. I can add 3 and end up here. I can end up 4 and I can end up here. Now, this only works with arrays. It doesn't work with our other data, okay? Because you've got to remember that our other data are just basic data types, okay? Where we know that these arrays come one after each other in memory. So that's contiguous memory. And so we are allowed to do this. If you try and do this with your normal data, you'll most likely result in undefined behavior. Okay. So now what's going to happen is we go pointer A plus 2. And that's not pointer A, that's pointer C. So we go pointer A plus 2, which gives us this one here. And now it would print out 3. Okay. No, it wouldn't. Now let's go and have a look at those evil square braces. So I could have also said, actually, let's do this. So now what I'm going to do is I'm going to write printf %d, and I'm going to write something a little bit different. I'm going to write pointer A 1. What gets printed now? Oh, sorry. Pointer A is still pointing to where it is. So pointer A plus 2. Okay, so pointer A is pointing at that 3. What gets printed out? So pointer A is pointing at the 3. So it's pointing at that second index. So it's actually going to print out 4. Okay, and the reason for this is that all these square braces is a shorthand way of writing this. Okay, so pointer A plus 1, remembering that we are adding 2, and we're dereferencing it. Okay, now let's go back to really basics, and let's see if we can make sense of those basics. So, and have a look at the square braces and see them, how easy they actually are, or how hard they are. So if I went something like this, let's say I did short W becomes my array 3. Okay. The value that would be stored inside of W is going to be 4, obviously. Okay, so W has 4. Now, if I rewrite it using my other notation, such that I write my array plus 3, remembering that my array points to the start, plus 1, plus 2, plus 3, and I get 4. Remembering that this is an address, and so I have to dereference it such that I can get the value. And that is all that those square braces are doing. Okay, these ones are a little bit different. Okay, the ones when you're declaring are a little bit different, but the ones that we use, that's all they're doing. So we can take another example of these right here. Let me just move them out a little bit so that we've got a bit more room. Yeah, so just move those over a little bit. And what I'll do is I'm going to erase this second one. And what we get is something a little bit interesting. So we get my array plus 2. Okay. Now, whenever we have an address and then a dereference, they cancel each other out. Okay. And the reason for that is that we've got my array plus 2. Okay. So we've got the address at the start plus 1 plus 2. So the address of this part. Okay. Because we're dereferencing it, we're talking about the value. And then we say the address of the value. So we're talking about the pointer again. Okay. So this here, all this is saying is my array plus 2. Okay. And that is just another way of writing the address of my array square brackets 2. All right. Are we all good so far? Does that make sense? So I'm just going to have a quick 2-minute break while you wrap your heads around that. All right. So no. So it's not the address of the 3. It's the address of the location of the 3. Okay. So it's not the address of 3. It's the address of the location of the 3. Because we're dereferencing, we're talking about this here. So we're saying the address of this. It's kind of like saying the address of A. We're not talking about what's inside it. We're talking about where it is. Okay. So it's not the address of the 3 itself. It's the address of this place. It's a bit hard to show because that's what the compiler does. So I can't fully evaluate it here, but I think you get the point. Yeah, so dereference is referring to this location and the value inside it. So if we get the address of that, where that 3 is, that specific 3, not any generic 3, then we know that's address. Okay, so when we dereference, we are actually talking about this. Okay, so all I'm doing is grabbing that address there. If I read the value, then I get a 3. Okay, so when I'm dereferencing, usually I'm just reading the value, but I can get the address still because I'm talking about that specific 3. I'm not talking about 3 in general. I'm not talking about a literal 3. Okay, because obviously that won't work, but this will, because in memory, let's say A had the value 3 in it. I'm talking about this. Okay. The same thing if I went and had a pointer. So let's say I had int A has 3. I have pointer B. Oh, oops, what am I doing? Int star B, and it had the address of A, and then I went int C, and I went what do I want? Oh, int star C. I could do something like this. I could go the address of dereferenced B. Okay, which just gives me B. Okay, so whenever you see that address and then a star, they just cancel each other out because all this is doing is it dereferences B, giving me this location, and then I grab the address again. So now it's a pointer again. Okay, don't worry too much about that. But when we're dereferencing, we're actually talking about that specific location. And we're grabbing the 3 from that specific location. And that's how we can grab the address. All right. Is everyone still here? If you're still here, put an emoji in the chat. Then we'll continue with maybe... what I might do is I might leave the pointer arithmetic to dynamic memory. It works both ways, but yeah, it's a bit better with dynamic memory because actually I probably do it with the mean. All right, so let me get rid of all this stuff because we don't really care about that anymore. What did I say I was going to cover? I completely forgot. All right. So what I'm going to cover now is just passing an array to a function using a pointer. So let's say I've got this function. Imagine that there's main and all that kind of stuff, and there's a function prototype. And I'm going to go float sum. Okay, so I'm just going to sum all the values up. And I'm going to go short star. Because this will be handy for the assignment. It's a summing function anyway. And I'll call it values. And I also need the size of the array. Okay. So here I've got my sum function. I'm going to create 2 more variables. Now, why is it a float? I don't need a float. I need just... I'll make it an int, just in case the number comes out larger, just for safety. Okay, if I'm adding a whole heap of shorts together, then the answer can become larger than a short. Okay. If I was doing a product, then definitely I'd go even larger than that. But here I'm not too worried. For I0, I less than n, I plus plus. All right, and then we'll go return sum. And then in here, we're going to go sum plus assignment values I. Okay. Is this legal? What is what legal? Oh, we need to set sum to 0 as well. Is what legal? All right. So we've got some function here called sum. It accepts a pointer, which is a short pointer, and it accepts the value n. Okay. Now the value n is the size of the array. Okay. And then the values is a pointer to the start of the array. Okay. So what we're going to do here is we're going to call this function using our array, but we're not going to pass it in worrying about square brackets and stuff. We're going to pass it in using pointers. And so what I'm going to write here is I need to create another variable. I'll create a variable called total, let's say, and I'm going to call sum. I'm going to pass my array. That's a perfectly legal pointer. It's a short star. Okay, remember my array points to the start, first memory address, so it's of type short star. And how big is the array? 5. Now you can, if you really want, you can do a size of my array divided by size of short, and that will also give you a size of your array. But I'm not going to worry too much about that because we won't really be using that. Okay. So that's another way you can get the size of. The better way to do this 5 is going to be with a macro. You can have a look in the videos for that. That's the hash define. Okay. I won't go through that now because it's very simple, and I think you can learn that in your own time. All right. So let's have a look what happens here. So we're running out of room. That's the first thing that happens. Get rid of all this. Get rid of all this. This. Okay. So in the scope of main, we just have, what is going on? In the scope of main, we just have this array at the moment. We're also going to have a total variable somewhere. I shouldn't leave much room for it, but I'll leave a little bit of room. And then what we do is we have our function. Okay. Now it has two parameters. It has a pointer, okay, called values, and it's a short star. And then we have an int called n, okay, and we pass my array, which is just a pointer to the start of the array. And then we have n, which is 5. Okay, as simple as that. We then create our I variable. We've got I, which is an int, and we've got sum, which is also an int. Sum starts at 0. We get to the for loop. I starts at 0, and we get to this sum becomes sum plus values I. Now, remember that this is just the shorthand way of saying values plus I, and we know I is 0. Okay, so we go away. Why is that? We basically just have dereference values. So if we dereference values, we get 1, so we add 1 to sum. We come back up, I increments to 1. And now we have values plus 1. Now remembering that this here is a pointer, okay? And so it's actually adding 2 addresses, which gives us this address. We dereference this address and we get 2. Okay? So we add 2 to sum. Now notice that we're not moving the actual pointer. Okay? We are doing the addition here, and we're not changing the pointer. We're not changing values. Okay? And so on, and so on, and so on. Okay, so the next loop, oh shit, that should have been 3. Next loop, we add another 3, we get 6. Then the next loop, we add the 4, and we get 10. And then the last loop, we'd get 15. Okay. Then we return that sum, and total would have 15 in it. Okay. And you'll notice that there was no moving of the array. Okay. And we could have changed the array while we're in there as well, okay, because we had a pointer to it. But what you'll notice is that we didn't need to pass the whole array. The whole array, even if it was 10,000 big, it didn't have to move. Does that make sense? So now it makes sense to say yes, and then we'll continue. I also want to know what is the legal. what's illegal. All right, so let's do this a slightly different way. I won't do it with a while. I'll just do it with a for. And yeah, I'll just do it with a for. Should I do it with a while? I'll do it with a for. All right. So I'm going to do something slightly different this time. I'm going to keep my I, and I'm going to keep my sum. And I'm just going to introduce another pointer. Okay. Now, the reason that I'm introducing this pointer is to now basically I want to do this using pointer arithmetic. And you're going to see this in lab 6. Okay. What happened there? And so let's go have a look at that. So what I'm going to do is I'm going to create a pointer called pointer position. I'll just call it pointer pos. Okay. Now, this pointer here has a special use, and we'll have a look at that in a second. And then all I'm going to do is, inside of this for loop, I'm going to change some things up. I might also bring this up so I've got a bit more room. Cool. So here I've got int sum, same thing as before, but then I've got this new pointer, which just takes the exact same address as the first address. Then inside the for loop, I'm going to go sum. I forgot to set sum to 0. Sum becomes dereferenced pointer pos. And then I'm going to go pointer pos plus plus. Oh, and plus equals, sorry. All right. So here we're going to do a little bit of pointer arithmetic using loops, just so you can see how it works. And also, you won't see the importance of this yet, but it'll make sense a little bit later why I create this pointer pos. All right, so I'm going to create my scope. The scope needs to be a little bigger this time. I've got my values once again, which is exactly the same as before. It's of type short star. I've got my n, just as before, which is n, and it's an int. And I've got this pointer. Might change the color because I'm going to be moving it around. Okay. And then I've got n, which is 5. Then I create another pointer. And this is my pointer pos. It's also a short star. It's pointer pos. And it just copies that same memory address across. Okay, so it's just copying that exact same memory address. So it's also pointing at 1. I have my I, as I have before, and I also need my sum. I didn't really need that much room. Sum, which starts at 0, is an int. And I've got I, which is also an int and starts off at 0 in the for loop. All right. So now we're going to have a look at what happens inside of this for loop. So sum becomes sum plus dereference pointer pos. So dereference pointer pos gives me 1, and I add that to my sum. Now, when you increment, the same rule applies with pointer arithmetic. So it's going to go up 2 addresses because we've got short. And so it's going to go across over to here. Okay. We then increment I as well. So we get 1 here. And we come back down. We dereference pointer pos, so we get 2. And we store that into our sum. Okay, so we're accumulating here. And then we increment pointer pos. Okay, so it's pointing there now. And this becomes 2. Okay, we're just following the rules of a for loop. Okay, just this part here. 2 is still less than 5. We dereference pointer pos, so we get 3. And we accumulate it with our sum, so we get 6. And then we increment pointer pos. So it's going to be here. This becomes 3. Okay. And then from here, we keep going. So we dereference that. We add 4. We increment pointer pos. So now we're pointing here. We increment I. Is 4 less than 5? Yes, it is. So we keep going in our for loop. We dereference pointer pos once again, and we get 5. Oh, shit. That should have been 10. So we should get 15 now. Okay. Sorry. And then we increment pointer pos. And this is important. And we'll talk about this in a second. And then we come back up, and I becomes 5. Is 5 less than 5? No. So we exit the for loop. Now we're somewhere around here, just before the return. Okay. Now, you'll notice that this pointer is pointing at something that it shouldn't. Okay. So it's pointing at a location that we don't know what's there. All right. We'll talk about that as well. So we don't know what is there. Okay. And that's okay as long as we don't read or write to it. Okay. Now, why did we use pointer pos? Well, there's a really big reason for dynamic memory, which we are not up to yet. But while I'm still inside this function, I've lost my array. Okay. If I didn't have these values, I do not know where the start of this array is anymore. Okay. So this can get really difficult, especially when you're moving backwards and forwards through your array. Always try and maintain the start of your array when you're using pointer arithmetic. Because if you lose the start of your array, you've got nowhere to go back to. Okay? So always make a copy at the start before you do any kind of pointer arithmetic so that you don't lose the start of your array. Because now if I wanted to do something else, I can just reset pointer pos back to the start and continue on. Okay, even if it was a complex thing where I was moving backwards, forwards, and over. This one's simple because we're just going straight through. I can still get back to a known state. Okay, so you'll see later where we can actually lose our entire array. Okay, but this is a practice that you should get into by making a copy, because inside of here, as soon as I move this, I don't know where the start is anymore. Okay, if I need to get back to the start while working in here, and I've stuffed something up, and these values of I and n aren't reliable for me to get back to the start, then I need to crash my program or exit unexpectedly. So always try and keep a pointer at the start of your array, and it just means that you've safely got somewhere to go if you need. And then we just return as before. Does that make sense? Yes. So later it will become extremely important because you can actually lose your entire array. But here, it's starting to get you into the practice of good practice. Okay. We haven't got to dynamic memory yet, but with dynamic memory, you don't get this guy. And so if you start moving it around, so one thing to note is that you cannot change this here. So I can't go my plus plus. Okay, it won't let you. The compiler won't let you change that. Okay, so the compiler will say no. Okay, so you've always got the first address when using arrays declared on the stack like this. Okay, and the reason for it is the compiler doesn't want to lose the start of the array. Okay, same thing, you should follow the same practice. Okay, cool. All right, so let's have a quick look at the stack and the heap. I'm just going to go over the really quick points about the stack and the heap. So basically, the stack is fairly small. Okay, this is a bit of memory that's fairly small, and you can crash it easily by calling too many functions. So recursion can cause it to crash. You can make it crash by basically having variable size arrays when you are running your program, which we'll have a look at in a sec. And it is fairly small. And so we need to be really memory conscious. The heap, on the other hand, is large. Okay. Yes, you can do that. That's perfectly fine. That's perfectly fine. Because my array 2 is just a pointer. It's not an array. And the complexities between those is a little bit interesting. All right, so we've got small and large. Now the stack, everything we declare is automatic. Okay, so it means that if we declare some memory, it's just kind of easy. Where when we declare on the heap, it's the programmer's responsibility. Okay, so this is a very, very different, because here when we declare something, it just automatically goes on the stack. We don't have to do anything. The other thing that we don't have to do on the stack is deallocate memory. So you'll remember when we hit one of these braces and I've declared something inside of here, it just pops off the stack and we got rid of that memory. We didn't have to do anything. We just ended up at this brace. And this is why we declare stuff inside here, such that when we reach here, it just automatically deallocates it and we have a bit more memory. Here, we have to do that ourselves. The other thing is that the stack is fast, where the heap is slow. Okay, but when you need large data or dynamic data, this is where you want to use the heap. Now, the most common mistake that people make when programming, and it shows in an experience, is when people do this. So, what do I want to do? Let's say int size printf, how big would you like your array? I should put some quotes there. And then they scanf that value. And then they do something like this. They'll go int array size. Okay, this is bad. Okay, all right, this is bad. Okay, this is dynamically allocating memory on the stack. Okay, which in most cases, as soon as you get it slightly large, it will crash the stack. Okay, and you'll get a stack overflow, and it won't work. The other thing is that with the stack memory, it's only available in that scope. So if you try and declare inside of a function or something, it won't exist when you try and bring it back. So that's another reason that this is bad. Okay, because you're trying to declare memory at runtime on the stack, and so it has a bunch of bad consequences. If it's something tiny, like less than 10, you can probably get away with it, but I would still probably shy away. If you're going to go with 10, if it's less than 10, just make an array of 10 and only use the first 3 if they only need the 3. Okay. So this is bad because it's just, let's say your stack's this big and the user enters something that's this big. Okay, it's fine, it's running. But if it goes above that, then it'll crash. The other thing that might happen is that you create that and it's like this, and then later in your program you create something else and then it crashes. Or you call the function and then it crashes. Okay, you don't want these dynamic things to be created at runtime on the stack. You want to use the heap. Okay. All right, I'm going to have a little bit of a break, a 5-minute break, and then we'll talk about how to create memory on the heap. Okay. And then once you've got that, you can start doing some really cool stuff on the assignment. We can have a quick look at that. Do part 1. I think I've covered everything. Well, we will cover everything for part 1. Yeah, pretty much. All right, so I'm just gonna have a quick 5-minute break. Go grab yourselves a glass of water or something, or a drink or whatever, and then we'll have a look at dynamic memory. Where is that thingamajig? All right, how we going? If you're still here, put some ducks in the chat. We'll get on to dynamic memory. The assignment. Yeah. And we'll be good. Can you hear me? Yeah. Where's the ducks? Ducks. Chicken. The ducks? I can't even find a duck. Oh, there we go. There's a duck. I lost it. Big duck. All right, so I'm going to just write out some stuff. I don't want to. I might type this just because make it a bit neater. Big. Yeah, I had a bit of trouble finding ducks as well. All right. All right, cool. All right, so we're going to start using another header file, and this is going to be standard lib.h. Okay. And this is something that you're just going to have to start adding. Okay, don't worry too much about why at this stage. I'm then going to include main. That doesn't really matter. All right. Now what I'm going to do is I'm going to ask the user a question. So in here, I will ask them a question. So printf, what do I want to ask them? I want to ask them, yeah, left justify would help. Thank you for that. How large array? And then, why does it keep doing that? That's better. And then I'm going to scan it in. So I've got int. Let's call it size. Let's not call it size. Let's call it. Let's call it large. Okay. I just don't want to use size because we're going to use size of, and I don't want to confuse you between the two. Obviously, with a real problem, it'd have a better name, but I'm not too worried about that here. Call it largeness. Kind of a weird one. Okay. So now we've got this here. Okay, so we've got this variable called large. I'm going to draw the scope, okay, of main. Okay, and inside that, I have this thing called large. Okay, and it's an int, and the user says that they would like their array to be, let's say, 5 large. All right. Not dimensions. Dimensions is a different thing. We'll get to multi-dimensions later. We're just going to focus on one dimension for now. Okay. So I don't really want to use dimension because it is the size. But I'm just using a different word just to differentiate. All right. So I want an array. And I want this array to be of type, let's say short again. I like short because it demonstrates everything without me having to write a huge amount. Ints are a bit long, cars are way too short. So short is a nice one. So I'm going to create dynamically an array of shorts. And how I do that is I first create a pointer. Okay. And I'm going to call it my array again. Okay. And then I'm going to call a function called malloc. And this stands for memory allocation. And inside of this, move this out of the way. Probably need a little bit more room. And inside of this, I'm going to write some stuff. So I'm going to write size of, what's the type? Short. Multiplied by 5. So what I'm saying here is that I would like 5 shorts. Okay? Because my array is going to be 5 shorts. So I need 10 bytes to do that. Okay? I need 10 bytes to hold 5 shorts. Now, by pointing to it using a pointer, I can make sure that I read that information correctly. Okay? So inside of memory, what you've got to remember is that I'm reserving 10 bytes. Now, if I read that as cars, then I get 10 cars. If I read it as ints, I get 1.5 ints. 2.5 ints. And so on. Where if I read it as a short, I get 5 shorts. Okay. So depending on this pointer and this size of here, I can change what this data is. Okay. Now the last thing here is just a typecast. It isn't necessary, but it's good for while you're learning because it means that the compiler will pick up a mistake. So just typecast it to whatever your pointer is. Okay. Oh yeah, sorry. We'll use large. So whatever your pointer is, just typecast it to that. Okay. It just means that the compiler will yell at you if you do this wrong. And so it gives you a little bit of a guarantee that you've done this right. Well, close to right when returning. Now, this pointer here, if it works, okay, my array, it's a type short star. And what you'll notice here with my box and pointer diagrams, I'll draw that just to there for now. The memory that's created, I draw outside of the scope. Okay. And I'm going to draw this slightly differently than I draw an array. Okay, because it's like an array, but it's not quite the same. Okay. So first thing to note is that none of these have names, okay? And I can't refer to the whole array like I did before, but I sort of can because I've got this pointer at the start, okay? What you'll notice is that every individual block of memory there. No, casting does nothing. It literally, you can get rid of it and it will still work. It's just a good check, okay? Because malloc returns a void star. So you just typecast it to double check that you've got that there and that there. And if you don't, then it will give you a warning message. Okay? That's all the casting means. You can use an index anywhere, and we'll talk about that in a sec. Now, at this stage, what we've done is we've created 5 shorts. Okay? Now, the important thing here is that we can also check if this worked. So if this failed, we just get null here. Okay, so you can always check if malloc worked by putting an if it's equal to null. Let me fix that up. It's become part of the R. Okay, so if it's null, then we can just say it failed, exiting the program, blah, blah, blah. Okay, if malloc fails, there's no point continuing the program. At that point, you've run out of memory, which is pretty significant. Okay, and I doubt you will ever run out of memory on the heap in this subject. You can try though. All right, so now we've got this, and we've got a pointer to the start of this blocks of memory. Now, with this, because this is just a pointer to the start, we can just use it like a normal array. So I can do something like, now remember these are all uninitialized, so we don't know what's in them at the moment. But I can do something like my array 2 has 4 in it. Remembering that this is just dereference my R plus 2. My R starts here, plus 2 should leave me here. Dereference it. I'm storing a 4 in there. Done. Okay. I can also do that on the left-hand side, right-hand side. It works just like a normal array. Okay. You can do your pointer arithmetic with it, but this is where if you lose the start of this array, you've lost it for good. Okay. You cannot get your array back. All right. If you lose the start of this array, there is no name for the start. Okay. So my advice is never, with dynamic memory, ever change this. Okay. Don't point it somewhere else. Create a copy. All right. So if you want to do pointer arithmetic and you want to move around, always just create another pointer and allow that to move around. Okay. Not there, sorry. We're up here. Okay. And that will just create a copy that goes to here, and now you can move it around as much as you like. Okay. The next really important thing is when you're finished with your array, at the end of your program, you need to free this memory. And all you need to do is just type free and then the name of the pointer that points to the start of this. Now, this gets a little bit more complex when we get into 2-dimensional arrays, but you don't have to worry about that until the 3rd assignment. Okay, so for the 2nd assignment, all you'll need to do at the end of your program is make sure you free all that memory. Now, this is important because this exists outside of scope. So it doesn't matter if you get out of the brace, this still exists. This is also why it's important that you don't lose this pointer by jumping out of scope. So for example, if I did this, okay, that's bad because I can't free it. So if it's going to be used in a limited amount of scope, then you need to free it within that scope as well. Okay, but for this assignment, you're pretty much going to have it right till the end. Okay, so you'll declare it right near the start of, right near the top of main, so somewhere around about here, and then you'll get rid of it right at the end. Okay, but you need to remember to free your memory at the end. Okay, and you can do this as much as you like. So for example, you could do something like this. You could go free my array, and then you could go my array becomes short star malloc size of short times 100,000. Okay, so once you free it, you can create another array which is larger or smaller. There's also something called realloc, which you can have a play with if you like. You don't need that in the assignment or in any of the assignments. Yes, of course. Of course, ask as many questions as you like. I'm trying to get through this quickly so we can get onto the assignment a little bit. But do I need to free pointer from other scope? So you're not freeing the pointer, you're freeing the dynamic memory. So you don't ever free pointer pos. You don't ever free a pointer that's just pointing to something within the stack. You only free dynamic memory, so a pointer that's pointing at that dynamic memory. So the only things that you should free are the things that you create with malloc. And if you create them in a different scope, okay, so if I had scope around here, then it's impossible to free this, because as soon as I leave this scope, okay, so I've got two scope braces around here. What have I done? I've got this memory here, but this pointer doesn't exist. And now you've got this memory on the heap that no one can get rid of until your program ends. And you're just going to be blocking up a lot of RAM. Okay? So some programs do this, and this is a reason that they do crash. You might have seen some old games that have done this, where they basically leave a whole heap of them on the heap, and the heap just gets bigger and bigger and bigger and bigger, and they can't get rid of it because they lose that pointer. So if you declare it within the scope, then you need to get rid of it. Another way, if you know that you're going to declare it within this scope, a better way to do it then would be to declare this, say, here, or just before you enter the scope, so that you still can free it later if you need. Okay. All right. Now, with the assignment, I'll just show you one mistake that a lot of students make. And this is just a bit of maths. So let's say in this example, it's not how large I would like the array. It's, well, let's say it's how large I want the array, but I want it to be double that size. Okay. All right. So if they enter 4, then I want 8 shorts. Okay. How would you write that? Actually, so question for the chat. If I wanted double of whatever they entered, so if they entered 2, I'd like 4 shorts. If they entered 4, I'd like 8 shorts. What would I change here such that I would get that correct? So put your answer in the chat. So I want to double whatever they enter. No realloc. No. Why is people writing realloc? Okay, so this is where a lot of people make mistakes because they'll write ×2 here. Okay, the problem with this is that it's actually wrong because we go 2 times large, which let's say is 4, times 2. So 2 times 4 is 8, times 2 is going to be 16. Wait. What do we want here? Oh, we need plus, sorry. Sorry, I didn't mean double. Okay, sorry about that. That's actually correct. Let me do it a slightly different way. Let's say I want 2 extra. Okay. Thinking of 10 things at the same time. Okay, so let's say I want 2 extra each time. Okay, now the common mistake here is to do a +2 here. Okay, sorry. So multiplication's fine because of the order of operations. This is where the problem comes about, is when you're using addition. So the problem here is that I want 10 shorts when I enter 8. I want 6 shorts when I enter 4. I want 4 shorts when I enter 2. So I want +2. Okay. So if I add the +2 here, the problem is that I get 2 times, let's say I pick the 4, +2. Okay. 2 times 4 is 8 plus 2, which is 10. Okay. And what I'll notice is that I actually needed 12 bytes for 6 shorts, but I only got 10. So if you need to do some arithmetic, always just make sure to put it in brackets. Okay. So this is the total amount of shorts that I need times by the number of shorts. Okay, so I mean the size of shorts. So this is the number of shorts or number of elements multiplied by the size of. Okay, so just make sure to use brackets there. Same with the multiplication. Yes, you could add to it. That would work as well. Okay, but this is a common mistake that people make in the assignment. So I'm just showing you here because I'll expect some people to do it. And sorry for confusing you. All right. Cool. Does that make sense? All right. Let's have a look at the assignment then, because I'm starting to get tired. And yeah, don't forget, free. Are we all good up to this point? Cool. All right, let's get the assignment up. Where is it? PES. Learning Management Use Support. Cool. Cool, your session is timed out. Please log in again. PS, beautiful. assignments. Actually, I have it on. I already have it open. What am I doing? I just updated it. All right, blah, blah, blah. All right, maybe I'll just get it on the screen, and then we'll go through some things in it. All right, so blah 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 blah. Assignment 2, 10%. You need Unix, you need LMS, you need Notepad++. Okay. Now there are 3 files this time, not 1, 3 files, and they're going to have the same names. Okay, so AC calculator part 1, AC calculator part 2, AC calculator _ part 3. No late extensions, requests for extensions, blah, 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 blah. All right, so let's move me out of the way. So there is now. So there was a little problem because of the system that I was using, that it was cutting off the last character. I fixed that now. You can see the sample outputs for part 1 and part 2. And the math examples, Bella's kindly done, and I'll put those up today as well, or early tomorrow. Okay, so all the information is there. The only thing that's missing right now is the password. I've just got to do a couple of little things before I put that up. All right, so it's broken up into 3 parts. This is important, and you need to follow this. If you send 3 parts that are fully completed, we're not going to trust that submission. Okay, we need to see that you did the first part, then the second part, then the third part. Okay, make sure that you don't overwrite your previous parts. If you do, you need to go back and remove the subsequent sections. So basically how this works is, the first submission will look something like this, let's say. Then you'll make a copy of that. Okay. And then you'll add a little bit more to it. Okay, and that'll be your second submission. Then you make a copy of that. And then you'll add a little bit more to it. And they're your 3 submissions. 1, 2, 3. Which links? I thought I just unhid them today. Let me double check. Yeah, the example outputs are there. The worked math is going up today, but not there yet. But all the example outputs are there. Let me see. It's okay. Yeah, cool. All right. So the problem's broken up into 3 parts. There's a little bit of maths to start, and as I said, yeah, we're getting there. I haven't even got the lab up yet. I'm trying to get a lot done the next 5 weeks or so. Yeah, I just said, Bella just finished writing them. The worked examples will be up either tonight or early tomorrow. Okay, they will be up, but not yet. The quiz, the labs, etc. for the following weeks, I'm still working on, and I will get there. There is a lot we need to do before then. All right. So basically there's some maths here. Have a read of it. Make sure you make sense of it. A couple of big ones that people miss is that there is a minus there. Okay, so just be careful of that. All right, careful of that minus. The other stuff is fairly self-explanatory. This is summation if you haven't seen this before. I'll cover how to do, well, we kind of already did summation. So summation is basically what we did just before, where we're going through a loop. No, don't be sorry. Don't be sorry. It's all good. I think where we're summing up totals. Same with this one, we're summing up and then inverting it. You need to remember about this little inversion. So if you haven't said -1 before, that's just 1 over something. Okay. Don't stress too much about the maths. We'll give you lots of help with the maths. Okay. So the worked examples will go up very soon. They're all ready to go. She's written them. I just need to rotate them and put them on LMS. And then we get to the first task. So you must include the standard IO and standard lib. No other libraries can be used. You cannot use math for this assignment. Okay, so if you have the math library, you need to remove it. You cannot use it for this assignment. You've got these function prototypes. You can't change these. Okay. These are required. Okay. Now you'll notice here that I've got the square brackets. This means an array can be passed in here. It's very similar to a pointer being passed, but it means that we can't pass this into here. It just helps you a little bit. We'll see how that works a little bit later. I'm not going to cover that right now. So we're calculating impedance, we've got print results, and then we've got 4 functions. Okay, these 4 functions here will look very, very familiar. They're straight from your lab 5, except for you need to change all these to doubles. Okay, so you just need to alter them from floats to doubles. You're welcome to change the naming, but you cannot change the types. Okay, so if you want to rename these however you like, you're welcome to, but you cannot change the types. Okay, so if it says double here and you want to change it to a short, no. Okay, if it says double star here and you want to change it to a float star, no. But if you want to name this something different, go ahead. But these names are pretty good. Don't forget the stars. Some people forgot the stars. The password will be there soon. The program asks the user for the frequency in hertz and number of components. It stores the results appropriately. All of these values are positive integers. You can assume the user enters any valid value for frequency and number of components. Yes. So you're copying them straight over to the assignment. Okay. This teaches you a little bit of code reuse. And plus, it means that we've been there to check these with you and make sure they work, which if they don't work, it makes this assignment extremely difficult. So this is why we did it in the lab. Okay, so enter the frequency, how many components are in the circuit. You know how to store variables, so you should be able to do that. Then we create 2 pointers to double variables. These combined form the result table. Okay? So here we've got result table impedance real and imaginary. Okay, so we're not just calculating the real and imaginary thing for one thing. We're creating it for a whole array. Okay. Now, with this, we're going to then dynamically allocate the memory using malloc with the size of double times the number of components plus 1. Now, I put it in brackets this year to make it a bit easier. Okay, so the plus 1 is for the total. All right, and you can see what the table looks like here. So if we had 3 components, we'd have 1, 2, 3, and then the total here. And we'd also need the exact same amount for the imaginary part. Okay, so index 0 will basically, for each of these tables, be a pair of real and imaginary. For the next one, it'd be a pair of real and imaginary, and so on. And then for the total, it'd be a pair. Then you've got to do the same for the length. Wait, not the length. Components, sorry. Okay, and the values of the components. Okay, so this will make a bit more sense when we have a look at this loop here. So basically, the user can enter 1, 2, or 3. You can use calloc. It's not really necessary for this problem. But if you want to use calloc, you're welcome to. So calloc just sets everything to 0 at the start. It's really good for counting tasks and stuff like that. It is slow because it has to clear memory. So if you know you're just going to overwrite that memory, then it's not really necessary. But you don't have to. If you want to use unsigned int, that's perfectly fine. When we say you can assume, it means that we are not going to test any values that are negative. Okay, we're not going to be evil and test your program using negatives or anything like that. Okay, if you want to use unsigned, that's perfectly fine. Or if you want to do some validation, which would probably be a better option, then you can do that as well. So you can put an if statement. If the user enters something wrong, then you loop and get them to enter something correct. But always do that last. Get the program working first. All right. So the user can enter 1, 2, or 3. Okay. And that is the type of the component. And that's going to be stored in this array here. Okay. So you're going to have an array with 1s, 2s, and 3s in it. Okay. Does that make sense? So you're going to have a bunch of arrays. Find a nice spot. Where's my pen? So you're going to have, let's say there's 4 components. Okay. You're going to have the first array is going to be the impedance real, which will have 5 doubles. Okay. And then you'll have the imaginary, which will have 5 doubles. And these are all dynamically allocated. Then you'll have the components, which will be 4. What are they? They're ints, I think. Yeah, 4 ints. And then you'll have the values, which are doubles as well. Okay. So they're 4 doubles. So the first one's going to have 1 extra because you've got the total as well. Okay. There's no component total or values total. Okay. So that's up to step 6. You should have that. When you get to step 7, you can start putting the stuff inside of the arrays that we created in 5 and 6. Okay. Once again, we're only going to give you valid stuff. So positive values and 1, 2s, and 3s. We're not going to throw a 4 or an 8 or something weird at you. We are just going to give you valid values. Okay. So you don't have to worry about invalid values there. Now, one thing you do have to worry about, if the user enters a 1, you'll notice that it says enter the size of the component in ohms. If they enter a 2, you have to ask the question slightly differently. You have to ask them in farads. If they enter a 3, you have to ask them slightly different again. You need to ask them in henries. Okay, they're the units of the different components. Okay, resistors are measured in ohms, capacitors in farads, and inductors in henries. Okay. Now, then we get to calculate the impedance values by calling the function, and we have the print results function here. Now, my advice is always to keep your program such that it compiles. Now, there's two ways to do this when calling a function. The first way is that you always just write the function before calling it, but sometimes that's not an option. And so what you can do instead, if you're up to this step and you just want to finish it off and just test that this stuff works, but you want to write the call to this function so you know where it is, what I recommend you do is go below main. Let's say your function's somewhere below main, and just put a printf in it, and just print not yet implemented. Okay. And the reason for doing this is so that you can still call func inside of main. And yes, it won't work, but it will compile. And when you run it, it just prints this reminder that you've still got to work on this function. Okay. This just allows you to maintain workable code. It tells you where that function is. It gives you a reminder that you need to add that still. So this is one way you can tackle your code while keeping it compiling, such that you can call your functions. The other way you can do it is never include a function until it's fully written. But sometimes that's not practical. Sometimes you want to call it even though it's not ready to be called, just so you can see the structure of your program. So either way is fine, but I do recommend this method, especially with an assignment like this. You can kind of work out where your functions are and just have it print out not yet implemented until you're ready for it to actually print. Okay, so that's a little bit of a handy thing you can do. All right, so calculate the impedance by calling the calculate impedance function, call the print results function. Okay, this is where a lot of students struggle. Okay, draw the box and pointer diagrams before putting in what you're going to pass to this function. Okay, because these two functions are a bit complex. And you need to think, do I need to pass the address? Do I need to just pass the pointer? Or what do I actually need to pass? Okay, so really have a think about it. Okay, don't just go and change all the types. I see a lot of students changing this to a double star and triple star or adding ampersands until it works. All right, really just slowly take step 8 and 9. Because if step 8 and 9 don't work, then neither is the functions that you're going to write after that. And neither will all of this. Okay? So just take it slowly. We can go through calling one of them maybe in a future help session. And then at the end your program appropriately, and it gives you a hint. Yeah, so if it returns a value, you just have it return 0 or something. Or if it's a double, yeah, you can return 0.0. Yeah, so just the dummy value is perfectly fine. All right, then we get on to calculate impedance. So here it says calculate the impedance for both the real and imaginary part for each component using a for loop where I is the index of the component in the array. Okay, so I think that's fairly self-explanatory. Basically, if we're talking about the first component, we're talking about index 0. Okay, if we're talking about the second component, we're talking about 1. Okay, makes sense. If component I, so if component 0, which would be the first one, is a resistor, then impedance real I is the size of the component, and the impedance imaginary is 0. So all this is saying is that if my component was 0 here, and let's say its value was 50, then its real part is going to be 50, and its imaginary is just going to be 0. Okay, so, oh, sorry, not 0. Resistors are 1. So resistors are 1. Capacitors are 2. And inductors are 3. Okay. So whenever we have a resistor, we just take the value straight away and put it in the real part and set the impedance to 0. But the imaginary part to 0. Okay. So if it's a resistor, impedance real is the size of the component, and impedance imaginary is 0. And we can see this in the formulas if you want to have a look at it in terms of the math. So resistor, the impedance resistor can be found as Z becomes R. You'll notice there's no J, meaning that it's 0. Okay, you could rewrite this as plus 0J. Okay, and we know anything multiplied by 0 just gives us 0. So the imaginary part is going to be 0, and the real part is just whatever the value is. Okay, so that one's nice and easy. The next one, if it's a capacitor, the real part is 0. Okay, so if we have a 2 here, okay, we can go straight ahead and put 0 in the real part. Okay, and then it says the imaginary impedance is negative XC. Have a look at the background information. So go up to the background information, and we get this XC up here. So we have this. So we need a value here. So we have XC becomes 1 divided by 2 pi FC. Okay. Let's say our F is 60 or something like that. Okay. And we also need it to be negative. So we've got negative 1 over 2 pi 60 times 20. Again, you calculate that and put that in there. All right. Don't forget that negative. All right. That's very important. All right. From there, we have. What's my phone? Sorry, just gotta check something. All right. From there, we have our inductor, which is just XL. Now there is no negative in front of this. We'll also notice that the real part is 0. Okay. So if we have an inductor, then the real part is 0. And if we go up to the reference information, once again, the XL is just 2 pi times F times L. Now, F is one of the values that we got at the start. That's the frequency. Yeah. What's the frequency in hertz? So the user could have entered anything for that. That's valid. So we have 2. So give it a value. Let's say it's 10. 2 times pi times 10 times 60. Okay. All right. And we said 4. So let's say they entered another capacitor. Okay. And they entered, let's say 1. This would be 0. This would be negative 1 over 2 pi times 60 times 1. Make sense so far? You think you can do that? I think you all should be able to do that fairly easily. It's not too difficult. Are we all good so far? I think I'm a little delayed. I'm quite delayed. All right, I'll give you a second. So at this stage, we haven't said anything in the total. So it's any number of components. For our case here, there's 4. It could be 2, it could be 100, it could be 10,000, it could be 10 million. It could be any value of components. Okay. Because we're using dynamic memory, we're allowing any number. But if you do set it to 10,000, you're going to have to sit there and write every single one. So they're going to be realistic values. Probably the largest is going to be about 10 components for our tests. But if you want to test 10,000, it still should work. Okay. So this is up to the user. It's dynamic. Okay. And you can have a look at the example outputs, and there's some with 5, some with 6, some with 3. I don't think I put any with 2. 1 should work as well. So keep that in mind as well. Now we're going to calculate the total impedance of both the real and imaginary part and store the result in those 2 spots. Okay, we've only got 2 spots empty, so that's where those results are going to go. So this goes back to our summation that we did just before. So we're going to create 2 variables this time for our sum, not just 1. Okay. 0 is not really a valid number of components. If you want to deal with that case, you can, but we don't really care. So for 0, it probably just should say there's nothing to calculate. It's not really valid for solving impedance. So I wouldn't worry about it. All right, so we're going to create 2 variables for sum, and we're going to iteratively add up the real parts and iteratively add up the imaginary parts. Now, if you want to do this as 2 separate for loops, you can, or you can do it as 1 big for loop. It's up to you. And then store the impedance values in the appropriate place. Okay, so basically all you're doing here is, where's my pen? I've lost my colors. That's why everything's black, because my head's over the colors. I have a habit of trying to change colors all the time. But... All right, so basically here, all we're doing is we just create 2 sum variables. So I might call this sum real, sum imaginary. Don't forget with your sums to always start them off as 0. We're going to have our I variable. We're going to have a for loop. And we're just going to have 2 sums this time. Okay, so sum imaginary plus, so accumulating, okay. And then at the end, store them in the right place. So you need to store them here and here. And so the real one should just add all of these up. Okay, so for this one, it's 50, so it's nice and easy. And for this one, it'll add all these up, which I don't know what the value is. It's something. Okay. So you just need something that looks like that, such that it adds all the real and imaginary parts up. Okay. Makes sense? All right. And then we get to the last part, which is printing the results. Print the results table as shown below. The first column describes the rows with the text. Oh yeah, because we haven't got up to that part yet. So here it just says components and then Z ohms. Okay. So that first row shows this. Now I'm trying to trick you here. Okay. Obviously, you should deal with the rows first, not the columns. Okay. Because we can't print downwards, we can only print across and then go to the next line. So I am purposely trying to trick you there, but you can work that out. So the first row prints out the components, R for resistor, C for capacitor, I for inductor. So you've just got a for loop that for this part here. So you can break this up into a couple of different parts. So let's have a look at it. Actually, what I'll do is I'll copy and paste that. And then we might finish up there. Green. All right. So from here, let's have a look at this and see how you break it up into code. So components is obviously by itself. So you're just going to print that. This part here in the middle, R, R, C, I, and so on is dynamic. So that's going to involve some kind of for loop. The total is always the same thing. So it's just going to be a simple print. Okay. Oh, damn it. Oh, well, let's just print another one. And then we get to the next line. We then print Z ohms. That, once again, is static. It's always the same. So we don't need a for loop for that. The stuff in the middle is obviously dynamic. So we need another for loop. And then the total at the end is always at the end. Okay, so you just print that by itself. Okay, and there's one new line here, and there's one new line here. Okay, and you can work out how to put all that together. Okay, and that's pretty much all of stage one. Okay, so once you've got that, you can test it, run it, etc. And then you can do, once you've done that, so only start once you've tested it 100%, it works. Don't bother going on to the next stage if it doesn't work, because we won't look at the next stage if it doesn't work. Okay, we'll always go with the lowest one. Yes, yes, total is at the end. Total is here. Yeah, if you want, you could include it in the for loop. It's perfectly fine either way. You can add one. You can't for the first line, but for the second line you can. I don't know. It's up to you. So yeah, you could combine both of those together if you wanted to. It's up to you. But you can't for the first one because it's not in the it's not in here, the total. So it's up to you. If you want to keep the same structure as you go along, versus having it there, it's up to you. Completely up to you. Whatever makes you happy. All right. I forgot what I was saying. All right, and then once you've done that, you can start working on part two. Part two, you'll notice that the print is exactly the same, and that Main only changes a slightly bit. So here you're going to create parallel series, and then you just have to change step 7 so that it sends that choice across. And you need to update this function prototype so now it has choice. Okay, so main and print result, there's very few changes. The big change here is going to be calculating the real and imaginary parts, because the sum is a lot more complex for parallel. So for series, it's just Z1 plus Z2, that total plus Z3, that total plus Z4, that total plus Z5, and we get a nice simple summation. However, for parallel, we're taking the reciprocal of Z1 plus the reciprocal of Z2, and then we take the inverse of that, and then so on and so on and so on. So we end up with this here. So we're basically just adding them up. Such that, where's my pen? Such that we go like this, and then we go like this. Okay. But in code, it's a bit more difficult, and also you've got the real part and the imaginary part that you need to do this to. So it's not just one, it's both. Okay, and I give you some hints on how to solve that, and I'll maybe discuss this a little bit later once you've done part 1. So try and get part 1 done before the end of the holidays, and then probably next Sunday we can go over this and get this done, or maybe earlier. Give it a go though. So it's just this that's different. So give it a go and see how you go with it. And then part 3 is where it starts getting a little bit more tricky, because now you've got your print results get a lot larger, because now it's got a lot more dynamic memory. So we don't just have the 2, we have 6, okay, because we're going to worry about current and voltage as well. Okay, so we started off with 2, but now we're going to have 6 here. Okay, and we don't give you all the information for the voltage and current. Okay, that's basically it. Same rules as last time, really, except for code must not crash or have the potential to crash due to Stack Overflow or segmentation fault. This is hard. Okay, if you don't understand your pointers, you're not going to know if it has the potential. Okay, and we will know. All right. Blah 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 blah. The examples are given on LMS. Same rules as before. Automatic deductions. There was a couple of people that didn't do this one last time, and they got 0. So it does happen. The rubric is different. So if it doesn't compile, you can't get these marks this time. There's very few that didn't compile in the first go anyway. Part 2, part 3, and then there's a couple for all parts. So documentation, unsafe behavior, variable types used where appropriate, variables limited to an appropriate scope. So we're worrying about scope this time. Variables named suitably for the code and domain. Code is indented correctly. And then the other ones are just things like mallocs used incorrectly, functions are used correctly, things are calculated correctly, values, memories freed, etc. So it is a little bit micro marking. There is 28 points for the third part. So if you don't get the third part done, the highest mark you can get is 72. So just be aware of that. Assignment due date. Why does everyone want to make the due date so early? So I'll see what people's progress is at the end of the holidays. Basically, with the due dates, so it was set for week 9, but if everyone starts it early and they're using it to understand the labs, and we can use it in the help sessions, and we can use it. And I see that people have completed part 1 by the end of the holidays, then I can extend it a little bit longer. If no one's starting it, if I don't see some early submissions, so remember we want to submit as often as possible, then I need to make it earlier to encourage people to do it. So with the due dates, it is dynamic. I can set it to the normal due date of week 9, or I can make it a little bit later if everyone starts early and make a better result. Yeah, so start it early and you won't have to worry about the due date so much. Okay. Yes, it is a lot harder. And this is why I want to encourage you to start early. And this is why I haven't worried about the due date yet, because if everyone's starting early, then I know that this assignment will do what it's meant to do, which is basically make the exam extremely easy. But if no one's starting it, then that didn't really have much of an effect, and I have to force people to start it early because it is a lot harder. All right, is there any last minute questions? Submit early anyway. I like to see, and I have a look. It allows me to have a look, and if I notice anything strange, I'll let you know. So, yeah. So before the end of the holidays, ideally, part 1 completed, part 2 attempted. And then hopefully I can hold another session, maybe next Sunday or something, go through part 2, get that out of the way, and then hopefully by week 8, end of week 8, you've got. Yes, you have to submit each part. If you don't submit each part, you won't get the marks for it. Okay. This is really important. Okay. So if you only submit part 3, even if it includes part 1 and 2, you won't get the part marks for 1 and 2. Okay. This just ensures that we know that you actually did this iteratively and you didn't just get it from somewhere as a big file. How can I use one function to calculate 3 types of impedance? Well, it's a for loop with if, else, if, else. If it's a resistor, use this formula. If it's a capacitor, use this formula. If it's a inductor, use this formula. Yeah, try and submit that before the end of the holidays. That'd be good. Okay. The earlier you submit it, the more I can have a look and see what people are struggling with. I would recommend it. Because what I usually find is that by the time people submit their assignments and then I start reading it, I might go, oh shit, I could have mentioned that. Or I could have said something about that. The earlier I see the assignments, I see the common mistakes. I see places that people are looking up on Google and stuff like that that just don't apply. And so we can address those issues before it's too late. All right. Any other last minute questions? Sorry, I was a bit tired this time, but I'll be full of energy after a bit of a holiday. Pretty much, but that will work. All right. Thank you very much. Enjoy your study break. Try and keep up with the stuff you're doing, and I'll let you know if I do another one before we return. Thank you very much for your time, and yeah, enjoy.